One of the most unobvious collateral benefits of cardiothoracic surgery is nothing scares you. Not a room full of people, not the tax man, not a gorgeous girlie you're sat next to on the bloody stage. Nothing. That's C Slater Slider, is it? Thanks very much for the invite, Pedro. I was really excited when I saw this, because making anything change in the medical profession in the UK is virtually impossible. And it is really, really encouraging to see a group of people putting something so powerful together as this can be. Very interested to hear Professor Hipple refer to necessity being the mother of invention. I would love to take credit for this, but of course I can't, because necessity was the mother of my invention. You see, I'm a chartered engineer, I'm a professional engineer, a member of the Energy Institute and the Royal Society of Chemistry. Like lots of patients, we're professionals. We're professional engineers. We may not be professional medics, but we can offer just as much professionalism and innovation, in fact, in some cases, much more than the medical profession can. So as a group, we are an incredibly powerful resource, and we've got to make them have it. We've got to go along and say, we can do this. Come on, work. Oh, there you go. What am I doing here? I'm a process engineer. I know all about combustion and air pollution control and stopping nasty things going up chimneys. What am I doing here? Well, I have Marfan syndrome. So I have long bones and long fingers and long arms, and I play bass guitar because I've got nice long fingers. But I also have a cardiovascular complication, which means I have a fibrillin deficiency, which allows my ascending aorta to dilate, to get bigger. If you look at this, this is the normal size of a normal human aorta. Virtually everyone in this room will fall into that band. The red line is at the start of this project when they would make a decision to go open you up and work on you. I went along to a genetic study in 1992 and had my ascending aorta measured, and I was a little bit alarmed by the dimension. And then I went every year and they took various measurements, and even though you can't see it, you see this perhaps as a graph, as a technical graph. Actually, this is a perfect representation of the psychology of denial. I spent the first, 8 years pretending nothing was going wrong. No, it's just noise in the data. You know, if you do some linear regression on that, it's flat, it's not changing. I got to 2000 and I was thinking, I've got to do something with this. I've got to do something, because what was on offer was pretty gruesome in terms of a treatment. So I went along to a patient support group day. There's an organisation called the Marfan Association in the UK, and they run an information day for patients every year. And I went along, and there was this guy, Professor Tom Treasure, talking about aortic surgery. So he gave the presentation on the existing options, which I'll tell you about a little bit later. And he said at the end of his presentation, any questions? So I put my little hand up and said, yeah, why aren't you scanning the aorta, CAD modeling it, using rapid prototyping to make a model, and then producing a perfect external support? And he said, what? And that was 14 years ago, and we're still colleagues, and we're rolling on. I recruited Tom as a medic, because I was not in the medical profession. Tom then got Professor John Pepper involved, another cardiothoracic surgeon. I put a team of engineers together. Warren was doing his PhD at Imperial College at the time and proved to be a great, in his word, CAD monkey, computer-aided design engineer. And that was the technical team which I put together to get the project going. Of course, you can't do anything without money. You can't do anything without money. Maybe not true of some of the innovations that some of the patients will bring to this patient innovation platform, but certainly if you want to do heavyweight cardiothoracic surgery, you've got to have money. We were turned down 3 times by a certain very well-known UK heart foundation, and I got no time for them at all. They're conventional, rigid, straight-laced people with no imagination and no vision. So I had to raise the money myself. So I bumped into an old school friend on the street in London, and said, oi, you're a rich bastard, I want some money for my project. So he introduced me to about 30 high net worth individuals. I did presentations, and hey ho, we raised the money. So we started a company. So I find myself not only as the patient innovator, but also as the technical director of a company that's manufacturing these devices. Don't forget that. Money is important, and profit is not a dirty word. We're not all greedy, grasping device manufacturers only interested in our next expensive car and holiday. Some of us actually care about the patients too. So the aim of my project was this. The only real problem with this aorta is it's a little bit weak in tensile strength. So if you can make a support that will fit around the outside, you can actually keep all of your own bits. You don't need to throw anything else away. You can just retain all of your native tissues, and that actually solves an awful lot of problems which occur if you go down the conventional surgical route. So it's really just about making something that's a perfect fit for your particular ascending aorta. This is what an ascending aorta looks like. You've got that the left ventricle is down here. You can't see it because there's no contrast agent in it. The aortic valve sits about here. This is the ascending aorta, and it goes up into the arch and then down to the descending aorta. And it's this bit which tends to be the problem because it's the largest diameter. And the problems you get with it as it stretches and becomes larger are, first of all, you might get the valve beginning to leak, aortic regurgitation. Secondly, you might get a bit of an aneurysm formed. Or in fact, you may get a dissection. A dissection is when the media, the principal structural tube within the aorta splits or tears, and then you're in trouble. You're in real trouble. If they operate on you, you've probably got about a 20% mortality associated with that. So it's a very high risk place to go. So what the medical world try to do is to work on aortas before they get to the point where they've dissected. This is a section down through the heart, just so you can see what we're working on. This is the left atrium receiving oxygenated blood from the lung. It drops through the mitral valve into the left ventricle. That's the main pumping chamber of the heart, which pushes it up through the aortic valve, up the ascending aorta, and round your body. So this piece of pipe we're working on, this ascending aorta thing, it's not bolted to the outside of the pump as a conventional engineering mechanical pump would be. It's actually incorporated within it. You can see that the bottom of the aorta there is pretty much in the center of the structure. So dissecting down around this pipe to access it in order to put this sleeve on is quite a challenge. A challenge not beyond the cardiothoracic surgeons, but it is quite a challenge. Tensile stress in walls, this is simple engineering, and it's pathetically simple engineering, and it applies in this case as much as it applies anywhere else, to the hydraulic hose on the brake system on the car you'll drive home, to the hose pipe in the garden. The tensile load in the wall, that's the stretching force that the Marfan syndrome is not very well able to manage, is proportional to the pressure and the diameter. That's why the largest section of your ascending aorta is the first piece to go. These are all, you can't really do much about blood pressure. You can take beta blockers or ACE inhibitors, but you've got to have blood going around you to stay alive, so you can't really change that. You can't do much about the diameter once it's got large, so the only thing you really can do to support this, to stop this thing getting any bigger, is to support it. In an unsupported aorta, you get a tensile loading in the wall of this aorta, and you can see it gets bigger and the wall thins. So D gets bigger, T gets smaller, so you've got an amplified increase in tensile load, which is very dangerous. If you put a support around the outside of it, you just get a little bit of compressive wall thinning. Now, fibrillin deficient media is much better at managing compressive loading than it is at managing tensile loading, as I'm living evidence of, because I'm 10 years down the line and everything is fine. So that's a little bit of the engineering for you. This is the standard treatment. This is a mechanical valve and a woven Dacron graft. And the standard treatment is they anesthetize you, open your chest, put you on a heart-lung bypass machine, cardiopulmonary bypass, stop your heart, drop your body temperature and stop your heart, remove the valve in the aorta and replace it with one of these devices. At the top, where you stitch this very strong tube to a very weak Marfan aorta, you get a ring, a stress point, which causes a lot of problems after the event. When they've got it in, they get all of the air out of it, they fill it all with blood, they get you back up to body temp, they get your heart working again, they take you off the cardiopulmonary bypass, they close your chest, and you're then on warfarin, anticoagulation therapy for the rest of your necessarily foreshortened life. So it's actually the fear, not of that operation, but of anti-coag, lifetime anti-coag, that just drove me to make this happen. So I didn't do this because I'm a philanthropist, I'm sorry to admit. I did it because I was terrified of the prospect of lifelong anti-coag. Any sort of impact, you're going to bruise badly. Any sort of skiing accident, road traffic accident, you're going to be bleeding seriously, and you're at significant increased risk with virtually anything you do that involves any sort of impact or physical contact. I'm a keen skier, I'm a keen deer stalker. I want to do these things, I want to live a life. I don't want to just sit there doing nothing because some medic says you can't do that. So that is what motivated me to make this project happen. I started with a functional specification. I don't believe in equipment designs, I believe in functional designs. What's this thing got to do? Well, what mustn't it do? You know, for example, it's got to remain flexible. It mustn't have any sharp edges. It's got to be totally compatible with the other materials and the biological materials and the flows and the pericardial fluid, blah, 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 blah. I spent about 3 months solid on this. A lot of time and effort went in. And the document that came out really did inspire and inform our thinking in terms of how we would go forward. I knew right at the start of the project what I wanted to do in gross terms, but I thought this would be a smart move just to make sure we got it right. So the first step really is to get decent images. CT scanning were at that time, I'm going back to 2000, 2004 now, relatively high radiation doses, relatively crude resolution, so I elected to go with MR because there's no ionizing radiation involved. We developed a scanning protocol. I spent, I don't know, 30 or 40 hours in the scanner at the Brompton. It's quite claustrophobic, but you kind of get used to it after a while. We developed a scanning protocol, and essentially we scan in ventricular diastole. That's when the ventricle is contracted and relaxed, and the aorta is shrunk back to its rest size. And we collect data right from the left ventricular outflow tract, that's the top of the ventricle, right up to the arch. And the full DICOM file output is just me bitching about software and standard file formats. We take out a particular type of file called a DICOM file. This is an example of the sort of image you can get from MR. This is a pseudo-SAG slice through me, that away. And you can see two of the leaflets of the aortic valve, there are three in fact, opening and closing quite nicely. This is the ventricle, and you can see the blood going up the aorta. And if you look carefully, you can see that when the ventricle contracts, the aorta stretches out and then releases a bit. It's actually a pressure accumulator. It's not just a pipe with a valve in. It's a smoother. It smooths the flow, the pressure pulse that runs up the aorta. This is a pseudo-trans. This is a slice through me horizontally. And you can see there the three leaflets of the aortic valve, all opening nicely, all coming back together nicely. And you can see it's all leaping about. That makes a big problem when you're trying to collect the images, for accurate images to make a model from. But again, you can see there that the valve is working fine. Even though I dilated quite a lot, the valve had accommodated and it was still working properly. That's something you don't get in real engineering. If you put it together incorrectly and it changes size, it just doesn't work. In the medical world, the body is infinitely adaptable. Perfect is the enemy of good, I think was the first thing the surgeons taught me. This is the kind of pseudo-SAG image that we would use to feed into our CAD program. Again, you can see that we've got the valve, the aortic valve down here, then the ascending aorta going up to the arch. And this was another type of image that we would use. So we would collect dimensional information from these various images and feed those into a CAD model. This is an early CAD model from one of the early versions of the program. And you can see it isn't bad. It's a little bit ropey, but it isn't bad at all. It helped us. We went through a series of iterations with the software to get to a point where we were happy. We were having regular monthly meetings with the two cardiothoracic surgeons, myself and the CAD engineer. So we went through some iterations to get to something that was okay, but we did get to something that was okay in the end. That gives you an idea of how we're actually doing this. We're not simply stacking slices. We're parametrically collecting dimensions from various points in the aorta and using those in our CAD package to produce the CAD model of the ascending aorta. That's a model of me. And you can see the one coronary orifice is in the right place and the other one has drifted up by about 1 centimetre. So as the aorta dilates diametrically, it also stretches on the outside of the curve. So all sorts of funny things happen. So even normal aortas are different. Diseased aortas are even more different one from another. When we've got the CAD model and the surgeons have approved it, we then use rapid prototyping to turn it into a solid physical model. So this is an SLS model, selective laser sintering, a lovely rapid prototyping technique. You drop the CAD model in, and 12 hours later out comes the finished device. We then use that. This is an example of a few of them from our 40-odd patients. You can see that whilst they all have a valve at the bottom and then a tubular curving section at the top, they're all different. This is why this particular personalized type of medicine has to be personalized. You cannot just make a generic device and slap it on anybody. You've got to do it on a personalized basis. With this program, with this CAD program and rapid prototyping, we can turn one of these round in about a week and a half at very, very reasonable cost. So it makes the idea of personalized medicine completely viable and totally doable. Once we produce that rigid former, we then produce the implant that's actually going to go into you, and that's a very lightweight textile that's that we form onto the surface. In my previous life doing air pollution control work, I'd done a lot of technical textile work on fabric filtration, and to my amazement I found that all of that knowledge base came into play when I was looking for the right material with the right function for this particular application. Unlike conventional Dacron grafts, no, Dacron isn't a real word, it's a trademark. They mean a woven polyethylene terephthalate graft, but they're surgeons, so they don't really know, do they? This is actually a knitted fabric, a knitted textile with a fascinating behavior that gives us all sorts of advantages for this application. For one, it's very porous, so pericardial fluid can move through it, and in fact, the device scars in. When you look at this device after 3 or 4 months inside, it's actually scarred into it. It is incorporated into the adventitia, the outside of the aorta. It's got no sharp edges, so where the coronary arteries come through it, where the surgeon cuts a little hole, there's no problem with a hard edge damaging a coronary. There is just no problem. You know, we're a long way down the road and we don't have those problems. And when the surgeon goes along with this device, he can install it in you without any cardiopulmonary bypass. We have used CPB on 2 patients out of 41. Me, because I was the first one, and John Pepper was a bit nervous. And one other patient who had anomalous coronary anatomy. They had one very short coronary artery, and it was safer for the patient to put the patient on bypass. But we don't need to use bypass or body cooling. The surgeon accesses the ascending aorta, fits this device. It can all be done in a relatively short time, and you're out and you're done. This is, again, an image of me. You can tell this one is post-operation because you can see the stainless steel wire that they use to wire up the sternum when they close you back up. As you can see, they look the same. The entire idea here is to retain the morphology, retain the shape. If you can retain the shape, everything's going to be okay. The valve will work, there won't be any dissections. I get scanned every year at the Brompton, and every year the images are always the same as the previous year, so I've just given up changing it. I could have put 2013 in there, but it would have taken me about half an hour to get the picture and put it on the slide and change 2010 to 2013, and it would look just the same. I kid you not, dimensionally there has been no change in 10 years. That's a very, very good sign. It means that the device is doing exactly what we wanted it to do. So the alternative is total root replacement, the one I showed you, where you have a mechanical valve, and valve-sparing root replacement, where the surgeon removes your own valve leaflets and puts them inside one of these Dacron grafts, compared here to personalized external support. Now, speaking as a patient who wants a short, safe operation, rather than a surgeon who wants to maintain his prowess over the rest of mankind and his proximity to God, I would say I would much rather a short operation than a long one. I'd really like not to have heart-lung bypass, CPB. I'd really like not to have any total body cooling. And I really don't want anticoagulation for the rest of my life. And I certainly don't want reoperation. These reoperation rates actually are quite conservative. A recent paper that's in production by Joseph Caselli shows that, in fact, even modern total and valve-sparing root replacement operations have perhaps a higher incidence of reoperation than that. This arises because there are problems with the valve, there are problems with the suture line around the top of the device, And believe you me, when a cardiothoracic surgeon's put a saw up your sternum once, you don't want it again. You really don't want it again. So, to me as a patient, this looks totally marvelous. This looks better than anything else, and I believe that it is. I don't believe that it is because I believe for the sake of believing. I believe because I can look at the evidence. So this month, we've got only 41 patients treated in 10 years, which is ridiculous, but shows you how obstructively conservative the medical profession, certainly in the UK, is. Between us, we've got a total of 170 post-op patient years. And we have, in that period, no device-related events. I'm at nearly 10 years, and I'm bored with it. I'm an R&D engineer, not a production engineer. I've had enough. I'm bored. I know it works. It's only the medics that haven't quite got round to understanding that it works. We've done patients of all different ages. Everybody's fine. So what am I doing here? A review on the surgery. We did have one death. That was due to a patient who had a very, very pronounced pectus excavatum. In Marfan syndrome, sometimes your ribs grow much, much too long. Your sternum sits very close to your spine, and therefore your heart sits displaced off to the left. And so accessing this guy's heart was very, very difficult. Whatever surgery he'd had, there would have been severe difficulties. And in the event, his left main stem, his left coronary artery was injured. They got him onto bypass very quickly, but he just never recovered. There were some other problems associated with him. And very sadly, he died about 5 days after the surgery. We never got a device on him. He was injured in the course of actually accessing his aorta. We've had one or two little funnies. One patient had what's called a pharyngeal flap, so we couldn't feed the transesophageal echo probe down his esophagus to look through his aortic valve during the operation. And we didn't quite get the coronary position quite right. They operated on him, closed him up, put him into intensive care, and he became a little bit arrhythmic. So they opened him up again, slightly adjusted the device, and he was fine. Another patient had anomalous coronary anatomy. He had a very short left main stem with a bifurcation and a coronary artery that ran round his aorta, and the surgeon wasn't aware of it. And when he put the device around, it clamped this artery closed, and of course the patient went funny. So they rumbled that very, very quickly, and then got the device between the circumflex coronary and the sinuses, and he was fine. The last one, we still don't quite know what went wrong. We actually opened the axial seam on the device after this particular patient's heart shows a strange rhythm. And they're all fine. I mean, there's not a problem. They're all fine, and they all have stable aortas. So we've achieved what we set out to achieve. Compared to the other two options, a 2-hour operation is so much better. If you're looking at how quickly the patient's going to recover and get back to totally normal living, and of course the cost to the healthcare, because elephant in the room, there is not an infinite resource financially here, and there's a serious risk, particularly in the UK, of our National Health Service going completely bankrupt because it just cannot afford the amount of treatments it's got to offer. So we have to think about money. It doesn't matter what you think about it, we've got to do it, or more people will die. The CPB is a big deal. I naively believed when I went into this that when you go into theatre and there's a cardiopulmonary bypass machine there, it's filled with a blood that's compatible with you. No. It's filled with a priming fluid. And to quote one of the cardiothoracic surgeons, when I complained a little bit after my 20 minutes of CPB, he said, well, of course, CPB priming fluid prompts just about every immune response the body's got. So if you can avoid CPB, you're going to recover much more quickly. And hey-ho, save a lot of money as well. 2 minutes, yeah, it's lovely. We're nearly there. I shouldn't use the word highly skilled. I'm a chartered engineer. I consider myself to be a reasonably skilled man with a reasonable skill in the art. But the surgeons and radiologists we've got are great. We've achieved our project aim. We've proven it actually on 41 patients. We've now got 4 surgical centres running. We're discussing moving it out to a number of other centres. It's all taken a little bit too long. We're not only applying it to Marfan syndrome there's aortic dissection associated with a whole group of other disease types. We've done bicuspid, a couple of bicuspid cases. We've done a transposition. We're looking at some Ehlers-Danlos lost Loy's Dietz. We're essentially thinking now, if your aorta is dilated, we can probably help you. We're also looking at the Ross procedure. That's something that we won't be concerned with here. I've got to thank a whole host of people, principally the man with an open mind. Tom Treasure is an amazing guy. I mean, without him opening the door to the medical profession, I wouldn't be here. I'd have a plastic valve and I'd be on rat poison. It's that, you know, it really is that simple. But our other surgeons, John Pepper, did the first 25 ops, fantastic guy. Mario, Philippe, Ulrich, Connell and David have also done lots of ops. If you want to find out more about it, go and look at the website. Thank you very much for your attention. Shall I show you? It's too horrible, isn't it? We won't show them the video. It's too horrible. Shall we? Yeah, go on, run it. Go on, run it. This is history. This is my chest open. My head's at the bottom, feet at the top. This is the first computer-designed.
I think so. Excellent. That's why I pulled it up to try and stretch it. I think if you stretch the pericardium, it helps.
Nearly 10 years ago. Cool. Thank you.